let me congratulate Dr. Rajesh Kandan for organizing such a lecture series on every Friday at 4 p.m., which will be really beneficial for all the new research scholars who are looking for nice problems to start up their work. And also, let me thank him for inviting me to deliver a talk on leech trees and some related concepts. So today, we'll be just seeing what is a leech labeling, some known results on leech trees, some classes of non-leech trees, and some other related labelings. That is, labelings which are related to leech labeling. So let me start with the preliminaries. First, we need to know what is a graph labeling. By graph labeling, we simply mean assign values either to vertices or to edges or to both. If we are assigning values to vertices, such labelings are called vertex labelings. And if you are giving values to edges, that comes under the category of edge labeling. And if we are giving values to both, then such labelings are called total labelings. There are a handful of well-known labelings. The first one must be graceful labeling, famous among all graph labelings. In graceful labeling, we are labeling vertices using values from 0 to m, where m denotes the number of edges. And when we are giving values to these vertices, that automatically induces a labeling on edges, and that labels must be from 1 to m. That is the condition. So we are assigning values from 0 to m to the vertices. The automatic labeling for the edge is the label of u minus label of v, taking the modulus value of the difference of labels of end vertices. And if that induced edge labeling gives exactly 1, 2, etc. m, such labelings are called graceful labelings. And maybe this is the well studied among all graph labelings. Then comes edge graceful labelings. Here we are giving values to edges from 1 to q. We are using edge labels. We are giving values from 1 to q. And from that, we get an induced label for the vertices. And these labels must be exactly from 0 to p minus 1. That is the condition. Here, p denotes the number of vertices and q denotes the number of edges. So that is edge graceful labeling. Then another one is harmonious labeling. Here again, vertices are labeled from 0 to m minus 1, so that edges also receives labels from 0 to m minus 1. So it is more similar to that of graceful labeling. Such labelings, if it exists, are called harmonious labelings. Coming to graph coloring, graph colorings can be viewed as a special kind of labeling. Here we are giving colors to the vertices. These colors can be considered as labels, or for colors we can say color 1, color 2, color 3, like that. That gives a labeling. And what will be the condition here? Here the condition will be that no two adjacent vertices must receive the same label. So that gives a proper coloring of vertices of the graph. So graph colorings are special cases of labelings. Again, if you take edge labeling, those come under the category of, if you take edge coloring, that is a special kind of edge labeling. And we have total coloring, which corresponds to total labeling. And there are many variations of graph colorings. Each of them are nothing but graph labelings itself. So let us move on to today's topic, leech labeling. Leech labeling is not defined for all graphs. Leech labeling is restricted to the class of all trees. There is a special reason for us to restrict ourselves to the class of all trees. So what is special about trees? Trees, as you know, are connected acyclic graphs. The connectedness property and acyclic property, both we are using here. Since it is connected, there will be a path between any pair of vertices. Since the graph is acyclic, that path will be unique. So trees can be viewed as graphs in which there exists a unique path between every pair of vertices. It is that property which we are using to define leech labeling. So, how many paths will be there in a tree on n vertices? Between every pair of vertices, there exists a unique path. So, from n vertices, I need to choose two vertices, which can be done in NC2 ways. So, trees are exactly those graphs which admit exactly NC2 paths. Now, we are going to assign values to edges, which means leech labeling is a special kind of edge labeling. Here we are assigning values to edges. What will be the restriction? The restriction is that all path weights must be distinct. So, what do you mean by a path weight? That name itself suggests a definition. You take a path, that path consists of a collection of edges, you add the edge labels, and what you get is the weight of that path. So in a tree, there will be exactly NC2 paths, and the path weight of these NC2 paths must be exactly 1, 2, etc. NC2. That is our restriction. Okay, so you have to give values to edges in such a way that the path weights are exactly 1, 2, etc. NC2. If such a labeling exists, we call such trees as leech trees. So here is an example, a simple one. Here you have a path on 4 vertices. I have already given the labeling as 1, 3, 2. We'll just check the path weights. Here there are 8 vertices. So how many paths will be there? 8C2. Sorry, here there are 4 vertices. So there will be 4C2 paths. That means 6 paths. So the path weights must be exactly 1, 2, 3, 4, 5 and 6. Let us check that whether it is true. Here we have V1, V2 path. This consists of a single edge and the path weight is 1. Now V3, V4 path gives a path of weight 2. Note that every edge is a path. Okay. So path of weight 3 is again here. 3 is an edge label. So V2, V3 gives me a path of weight 3. Now consider the path V1, V3. So what will be the path weight? 1 plus 3, which gives 4. So 4 is a path weight. Now V2, V4. 3 plus 2 gives 5. So we have a path of weight 5. And then the full path V1, V4. 1 plus 3 plus 2 gives me 6. Okay. So there are 6 paths, each of weight 1, 2, 3, 4, 5 and 6. So P4 is a leech tree and here you have a leech labeling of P4. Of course, the labeling need not be unique. Maybe you can find a different labeling. And obvious way of doing it is say write 2, 3, 1. You can interchange 1 and 2. Still, the labeling will be a leech labeling. In the case of P4, these are the only two possibilities. Either you can say 1, 3, 2 or 2, 3, 1. Okay. So that is leech labeling. The concept was introduced by John Leech in his paper Another Tree Labeling Problem, which was published in American Mathematics Monthly in the year 1975. So many years passed on, but there are only a handful of papers in this concept. So let us check which are the non-leech trees. Here you have 5 leech trees. These 5 leech trees were given by John Leech himself in his first paper. And he has mentioned that it is having some application in electrical engineering. Uh, he has not explained it in full detail, but if we can find leech trees, those leech trees can be used to build good electric networks. That was his concept. How we can easily find the fault in that network using this variation in the pathway. That was his concept. But what happened is that these are the 5 leech trees given by John Leech in his first paper, in his pioneer paper. And till date, we are not able to find any other leech tree. What is expected is that these are the only 5 leech trees. So that is an open problem, or maybe I can say leech tree conjecture. Prove that these are the only 5 leech trees. We'll just quickly look on these leech trees. The first three are too simple. The third one I had already explained. And then comes K1 tree. Here we have 1, 2, then 1 plus 2 gives 3, 4 is an edge weight, 4 plus 1 gives 5, and 4 plus 2 gives 6. So 1 to 6. 4 vertices are there, so 6 paths will be there. We have obtained all path weights from 1 to 6. Then comes this one. This is a Bistar. The definition we will see later. Here again, 1 is there, 2 is there, 1 plus 2 gives 3. This is 4. 5 is also an edge weight. Then 5 plus 1 gives 6. 5 plus 2 gives 7. 8 is an edge weight. 4 plus 5 gives 9. 4 plus 5 plus 1 gives 10. 4 plus 5 plus 2 gives 11. Then 8 plus 4 gives 12. 8 plus 5 gives 13. 8 plus 5 plus 1 is 14. And 8 plus 5 plus 2 is 15. Here we have 6 vertices. So there will be 6 into 15 paths. And we have seen that all pathways are attained by some of the paths in this. So this is again a leech tree. So these are the 5 leech trees dawn till date. If you are able to find one more leech tree, then you can go on for a publication. Okay. Let us have a look on what are the properties of leech trees. As I have already mentioned, we need paths of weight 1, 2, etc. up to NC2. The first point is we need a path of weight 1. To have a path of weight 1, it is compulsory that we give the edge weight 1 to one of the edges. We label one of the edges as 1. So definitely there will be an edge of weight 1, labeled 1, which we also call as weight 1. Okay. So 1 will definitely be an edge weight. What about 2? We need to assign distinct values to edges. So I can't obtain 2 as 1 plus 1 because the weight 1 can be given only to one edge. So to have a path of weight 2, it is compulsory that we need an edge of weight 2. Okay. So there will be an edge of weight 1 and there will be an edge of weight 2. Suddenly you may think that, okay, the path weight 3 is attained, but that is not true. If 1 and 2 are given, the weight 1 and 2 are given to 2 adjacent edges in a tree, then we have obtained the path having weight 3. But there is all chance that 1 and 2 do not sit nearby, they fall apart. Then in that case, again we will need an edge of weight 3. So regarding 3, we can't be sure. Either we can have an edge of weight 3 or it is that the 1 and 2 are nearby and that gives a path of weight 3. Both cases arise. Okay. Now, what about the path having weight NC2? For sure, we can say one thing. The path of weight NC2 will be a maximal path. Please note that it is not compulsory that it is the longest path or it is the diametrical path. It is not necessary. But for sure, it will be a maximal path. What is the difference between being maximal and maximum? There can be more than one maximal paths in a tree. Maximal just means that there is no path which contains this path. That is it. That's the concept of maximal. When coming to maximum, we mean that the number of edges is maximum. There is no path of length greater than that. That is maximum. And here what we say is maximal. So NC2 will be the weight of a maximal path. If not, what happens? There will be a longer path which contains this path and the weight of that path will be definitely greater than NC2, which is not allowed. Okay. So NC2 must be the path weight of a maximal path. And please note that that path need not be a maximum path. For the 5 examples which we have, both of these coincided. But in general, it need not be true. We can't use such a technique to prove that there exists a leech tree or there does not exist a leech tree. Okay. So using this third point, we will check which paths are leech paths. So we are moving to leech path. As we have already seen, P2, P3 and P4 are leech paths. What about paths of length more than 3? That is from P5 onwards, whether there will be any more leech paths. So what are the points which we have? The path of weight NC2 will be a maximal path. And the only maximal path in a path of length n is that path itself. So the weight NC2 is the path weight of the full graph of Pn itself. In Pn, how many edges do we have? We have edges, n minus 1 edges, right? In Pn, we have n minus 1 edges. And these n minus 1 edges must be given distinct labelings. Distinct means minimum it is 1, 2, etc. n minus 1. That is the minimum possible choice. Okay, if it is 1, 2, etc. n minus 1, what will happen? The total weight will be 1 plus 2 plus etc. plus n minus 1 in some order. And what is 1 plus 2 plus etc. plus n minus 1? Sum of first 10 natural numbers is n into n plus 1 by 2. So here we have n minus 1 natural numbers. So the answer will be n into n minus 1 by 2, which is precisely NC2. So from that, we can be sure that the n minus 1 edges are labeled using the numbers 1, 2, etc. n minus 1 in some order. Regarding the order, we don't have any idea. But the edge labels are definitely 1, 2, etc. n minus 1. Okay. There is an edge having label 1, right? And there will be some other edge adjacent to it. You take that edge, let the weight of that edge be k. So what will be the path weight of that path which contains these two edges? It will be 1 plus k, right? We already have edge weights from 1 to up to n minus 1. So this k plus 1 must be at least n. Otherwise, a path weight will be repeated. We already have paths of weight 1, 2, etc. n minus 1. And if k sits near to 1, k plus 1 is a path weight. So that path weight must be greater than n minus 1. It must be at least equal to n. But we know that the value of k is less than or equal to n minus 1. Edges are labeled using values from 1 to n minus 1. And k plus 1 must be at least n. So what is k? K must be equal to n minus 1. So from that, we can conclude that the edge which is having value 1 is a pendant edge. And the edge which is adjacent to that is labeled with n minus 1. Okay, so what is the case now? We are trying to find a leech label for a path. Now we have understood that 1 is the edge weight of a pendant edge. So path is having symmetry. So without loss of generality, I can assume that 1 is given to V1, V2. And the edge which is next to that must be labeled as n minus 1. That also we know because the sum is k. If this is labeled as k, I get a path of weight k plus 1. And k plus 1 must be greater than or equal to n, which means k must be greater than or equal to n minus 1. And what are the possible values of k? K can vary from 1 to etc. n minus 1 only. That already we have seen. Okay. So the edge next to 1 is labeled n minus 1. Now we know that there exists another edge of label 2. Okay. So near 2, there will be an edge. If the label of that edge is say again k or say k dash, then 2 plus k dash is the path weight of that path. Okay. This 2 plus k dash must be greater than or equal to n plus 1. We already have edges labeled from 1 to etc. n minus 1. So that cannot be a path weight of any other path. And here we have a path of length n. So that again cannot be the path weight of a path which contains 2. So this 2 plus k dash must be greater than or equal to n plus 1. Which means again k dash must be greater than or equal to n is 1. Okay. So 2 is adjacent only to an edge which is labeled n minus 1, and 2 is also a pendant edge, which means I have to write 2 here and conclude. 2 is a pendant edge, so I can't extend further. 1 is a pendant edge, so I can't extend in this direction also. Both are very particular that n minus 1 must be near them. Okay. So that settles the case. There are no leech paths of length greater than or equal to 5. So the only leech paths are P2, P3 and P4. And for all these 3 graphs, we have already obtained the labeling, so they are leech paths. Okay. When we are dealing with trees, the simplest case is that of a path, and another simplest case is that of a star. We take K1. So which stars are leech trees? That is the obvious next question. Again, for stars, we have symmetry. So we can start labeling with any edge. So without loss of generality, I label the first edge as 1. We need at least one edge which is labeled 1, right? So I take V1 as 1. Again, we need at least one edge which is labeled as 2. So I label V1, V2 as 2. Again, without loss of generality due to the symmetry. So these two edges together gives me a path of length 3. So 1, 2, 3. That many cases are settled. Now I need a path of weight 4. The only choice is to give 4 as an edge weight. So I give V1, V3 the weight 4. Now when I have given 4 here, this 4 plus 1 gives a path of weight 5 and 4 plus 2 gives a path of weight 6. Now we need 7, right? So next edge I am labeling as 7. Now 7 plus 1 gives 8, 7 plus 2 gives 9 and 7 plus 4 gives 11. So the value 10 is missing. I need 10 as a pathway, and the only possibility is to give label 10 to an edge. But then what happens? 10 plus 1 is 11, 7 plus 4 is also 11. So the pathway 11 is repeated, which is not permitted, which means I can't continue further. So 1, 2, 4, up to 1, 2, 4 it was okay. We were getting pathways as 1, 2, 3, 4, 5, 6. But when I try to label this edge as 7, the number 10 went missing. Okay, so from that stage onwards, for the labeling is not possible for stars, and hence the only leech stars are K11, which is same as P2, K12, which is same as P3, and we got one more, K13, which was the fourth among the list of all leech trees. Okay, so that is the case of leech stars. Now, after the first paper in 1975,
excuse me.
yes, yes.
Can you extend this to graphs that there exists a unique shortest path between two vertices, what are called the geodesic graphs?
Yes, we can. It is possible. It is possible, and we are working in that direction. And it is possible even to extend to other graphs also. We can take all possible paths between all possible vertices, but since the number of paths are unknown, such an extension is more difficult. But in the case of geodesic graphs, it is more easy to extend in that direction.
Yeah, immediate generalization of a tree could be a geodesic graph and a block graph.
Yes.
These are the immediate possibilities, I suppose. I don't know.
Yeah, and the concept has already been extended to forest also.
Okay. Oh.
So after 1975, there was a silence for 2 years till 1977, and then Taylor published 2 papers, one in 1977 and another one in 1981, maybe an extension of the one which he published in 1977, which contains an interesting result. The paper title is Odd Path Sons in an Edge-Labeled Tree, which was published in Mathematics magazine. Let me take you to that result, and then I'll tell you why it is interesting. That result is regarding the order of a leech tree. So what will be the order of a leech tree? Is it possible that there exists a leech tree of order 10? Or is it possible that there exists a leech tree of order 100? Such question. Okay. So assume that I have got a tree which is a leech tree. Here, d of xy denotes the path weight of an xy path. So my assumption is that I already have a leech tree, which means I already have a leech labeling for that tree. In that particular labeling, let d of xy denote the path weight of xy path, not the distance between x and y, but the path weight of the xy path. Okay. You start with any vertex tree. You take any vertex tree. Let it be a pendant vertex or let it be the central vertex or whichever vertex you want. You start with any arbitrary vertex tree. Color that vertex as black. So V is colored black. Now, all vertices which are at an even distance from V are also colored as black. Not that your distance means path weight of xy. Okay. So all vertices which are at even distance are colored black and all vertices which are at odd distance are colored white. Every vertex will be either at odd distance or even distance. So now we have colored all the vertices. Let B and W denote the number of black vertices and number of white vertices. Every vertex is colored either black or white. So B plus W is equal to M. Okay. Now, an xy path is of weight odd means what? What about the distance of those vertices x and y from the vertex V? The distance between x and y is odd. So either the distance between V and x is odd and V and y is even or vice versa, right? So if one vertex is colored white, the other will be colored black. So if an xy path is of odd weight, then the end vertices will be colored with opposite colors. Okay. So number of paths of odd weight will be equal to P into W. You give me any path which starts from a white vertex and ends in a black vertex, then the path weight will be odd. So number of odd paths equal to one end vertex must be black and other must be white. So B into W. Number of odd paths is equal to B into W. We have D plus W is equal to N and D into W is equal to NC2 by 2. Why? We are dealing with a leech tree, so the number of odd paths will be half, right? So here we are splitting into two cases. NC2 is even, that is one case, and NC2 is odd is another case. If NC2 is even, the number of odd paths is exactly half. That is n into n minus 1 by 4. Okay. So B into W is equal to n into n minus 1 by 4 and B plus W is equal to n. From that I can compute B minus W. B minus W whole square is equal to B plus W square minus 4BW. You just substitute and simplify. What you get is B minus W whole square is equal to n. Okay, that is the case where NC2 is even. Now consider the case where NC2 is odd. If NC2 is odd, the number of odd paths will be greater, right? Number of even paths will be 1 less than that. We start from 1 to NC2 and both 1 and NC2 are odd. Okay, so number of odd paths in this case will be NC2 plus 1 divided by 2, which on simplification gives me n square minus n plus 2 by 4. So in this case, B into W is equal to n square minus n plus 2 by 4. Again, you find B minus W whole square using the same formula. B plus W is n and BW is this. Substitute and simplify. What you get is n minus 2. Okay. So if NC2 is even, we have B minus W whole square equal to n. And if NC2 is odd, we have B minus W whole square equal to n minus 2. What is there in that? Actually, we have proved that the order of a leech tree will be either a perfect square or a perfect square plus 2. Whatever be B and whatever be W, B minus W whole square is a perfect square, right? In this case, we have n equal to B minus W whole square. In this case, you have n equal to B minus W whole square plus 2. So the order of an order of a leech tree will always be either a perfect square or a perfect square plus 2. So if you ask me, does there exist a leech tree of order 10? I can immediately say that the answer is no. There can be a leech tree of order 9. There can be a leech tree of order 9 plus 2, that is 11. But there won't be a leech tree of order 10. And what will be the next possibility? The next two possibilities are 16 and 18. Then you have 25 and 27, like that. Okay, so we need only search for a leech tree among the graphs of order, either a perfect square or a perfect square plus 2. So up to 6 we have already dealt. So the next question is regarding leech trees of order 9 and 11, and that problem is also settled. It has already been proved that there are no leech trees of order 9 and order 11. From 16 onwards, the question is open. Using computer programs, we have verified that there is no leech tree of order 16 or of order 18, but an analytic proof, a logical proof is still missing. So from 16 onwards, a logical proof is an open question. The only thing that we have is P is a leech tree implies P, the order of P, that is N, is a perfect square or a perfect square plus 2. So then coming to bistars. Bistar means the trees of this form. Okay, there will be an edge UV, and U will be having a collection of pendant vertices, pendant edges, and from V also there will be a collection of pendant edges. We denote it by BMN, where M is the number of pendant vertices adjacent to U, and N is the number of pendant vertices adjacent to V. So such graphs are called bistars and denoted by BMN. So we were looking up till the content was from literature, and from this point, this is my work together with Professor Arumugam and one of my research scholars, Sina Varghese. So we were looking for bistars. Again, we used a technique similar to that of a tree. We exhausted all cases. So there will be an edge of weight 1. Here we don't have a complete symmetry. So one can either be the edge weight of UV, or it can be the edge weight of a pendant edge. Two cases arise. Here I have taken the first case. So 1 is given here, which means 2 is the edge label of a pendant edge. It can be either here or here. Again, due to symmetry, we are free to choose that. So we place 2 here, and that gives 1 plus 2, which is equal to 3. Now we need to give the weight 4 to an edge. It can be either here or here. So from this point, we have two different cases. First, we will take the case where 4 is given here. So 4 plus 1 is 5 and 4 plus 2 is 6. We need an edge of weight 7. And if we give 7 here, in the next step, we will get a contradiction that 10 cannot be assigned. If we assign 10 here, 11 will be repeated. If we assign 10 on the other side also, 11 will be repeated. So I can't label 7 here. I need to put 7 on the other side. Okay, so let us try that. We put 7 here. So 1, 2, 3, 4, 5, 6, 7 and 8 is available, but 9 is missing. But when you try to assign 9, again you can see that duplicates pathways. So it is not possible. The next possibility is give 4 to the other side. Again, 6 cannot be assigned. Okay, 4 is in this side means 1, 2, 3, 4, 5. Then comes a path of weight 7. The path of weight 6 is missing. You can't assign 6 here or here because 6 plus 1 gives me 7, and again 2 plus 1 plus 4 gives me 7. Okay, and there is some other technique used to exhaust all the cases. This is probably the simplest case, giving the value 1 to the central edge. When we move on to giving the value to a pendant edge, so many cases arises, and we require some lemmas to exhaust and prove that there are only 5 bistars which are leech trees. Why bistars is interesting is that we have already 5 leech trees given by John Leech. All these 5 leech trees are bistars. They are B00, B11, B22, B10 and B20. Okay. So the leech tree conjecture can be restated as these 5 bistars are the only leech trees. Okay. Now this gives a picture of what is known about leech trees. The case of paths and stars are settled in 1975 itself, and Taylor proved that every leech tree will be of order either a perfect square or perfect square plus 2. Then I told that the cases 9 and 11. There are no leech trees of order 9 and 11 settled by this group in 2005. The case of Bistars, we have done. This manuscript is now online ready and will soon appear in print. And the case where a path with one pendant edge attached to any of the internal vertices. That is also we have completed, and that manuscript is under preparation. Not in a final stage. We will be communicating that soon. And the case of tri-stars, that is, you take a P3 and attach as many pendant vertices as you want to any of the three vertices. Actually, what we are looking is that stars means of diameter 2, path means diameter n minus 1. So the case where diameters 2 and diameter n minus 1 are already settled. So why not we try for other diameters? That is why we moved on to tri-star and we tried a pendant edge attached to a path in any of the intermediate vertices. Like that we tried. Thinking that maybe using the concept of diameters we can settle the conjecture, but still, till time we are unable to settle that. Okay. Now let us quickly have a look on some leech-like labelings. There are some labelings which are similar to leech labeling, namely minimal distinct distance trees, then modular leech trees, leaf-leech trees, and almost leech trees. So let us see what these concepts are. The first one is minimal distinct distance trees. By a distinct distance tree, we mean that we need to assign values to the edges, and with that we get pathways. All the pathways must be distinct. In the case of leech trees, it must be exactly 1, 2, etc. NC2. But here what we want is that all the pathways must be distinct. As I already told, Leech introduced the concept assuming that if you find leech trees that can be applied to electrical networks, so that the fault in a network can be identified using the concept of pathway. The pathways are all different, 1, 2, etc. NC2. So from that we can identify the path or circuit where the fault has occurred. Like that, it was his concept, but we don't have any other leech trees apart from the just 5 leech trees which we have listed, so that cannot be actually practically applied. Okay. But it is not necessary that the pathways are exactly 1, 2, etc. in C2. Even if the pathways are distinct, maybe we can apply the technique to find the fault. So thinking in that direction, the concept of distinct distance trees was introduced. So all the pathways must be distinct. But that is easy, right? You can say give pathways using very large labels. Say I take if there are 10,000 vertices, I am using labels as 10,000, 20,000, 30,000, etc. Then obviously pathways won't be repeated. But that is not interesting, right? So we need to find a labeling such that the maximum weight of a path is minimized. Okay, we need all pathways to be distinct, which can be done easily, but make sure that you have done it in such a way that the maximum path weight is the minimum possible. Okay, and for a tree, the parameter m of n, maximum distance in a minimal distinct distance tree on n vertices. It is denoted by m of n. Okay, you are taking all trees of order n and finding a value capital N such that we can always find a distinct distance tree labeling for that, in which the maximum path weight is less than or equal to m. Okay. This concept was introduced by these 4 people in the paper Minimal Distinct Distance Trees, which was published in JCMCC in 2007. And in that paper, as you can see, if that value of m of n it is equal to NC2, it means that you have obtained a leech tree, right? So such minimal distinct distance trees they call as perfect distance distinct trees. But this perfect distance distinct trees are nothing but leech trees. Okay. So leech trees are named as perfect distance distinct trees in this paper. And in that paper, they have computed the value of m of n up to n equal to 10. And for n greater than 10, they have obtained some bounds, but they haven't claimed that these bounds are strict. Maybe that you can find a better upper bound, or maybe that you can find the exact value of m of n for some n greater than 10. Both these questions are open. Again, in that same paper, as I already mentioned in response to a question from Professor Ampar Vijay Kumar, the concept has been extended to forest. Here you are taking parts only in the connected components. Each connected component is a tree. So if the number of vertices in the components are n1, n2, n3, etc., then the number of distinct parts will be n1z2, n2z2, n3z2, etc. So the number of parts is known. It is not equal to nc2, it will be very much less than that. Again, the definition moves on in the same direction. The path weights must be exactly 1, 2, etc. n1c1 plus n2c2 plus etc. plus nk-c2. So that is the concept of a leech forest. This was also introduced in this same paper. Then comes modular leech trees. In modular leech trees, edge weights are taken from ZK and the addition is done modulo K. Okay, so if it is difficult, say you are given a tree on say 15 vertices, you want to find a leech labeling, but it is difficult to find a path of weight 4. No problem, you can find a path of weight 19 and take modulo 16 to make it a path of weight 4. So conditions are a bit relaxed. So there is more chance to find modular leech trees than leech trees. Okay. So modular leech labeling was also called as ZK leech labeling. So we are taking edge weights from the set ZK. The concept was introduced by David Leech and Michael Walsh in the paper Generalized Leech Trees in JCMCC in 2011. Here you have an example of a modular leech tree on 6 vertices. So here you are taking the value of k as 16. You are taking the edge labels from the set Z16. So you are taking modulo 16. Okay. So let us quickly check whether all the path weights are there. Here 1 is there, 2 is there, 1 plus 2 gives me 3. Then what about 4? 4 is missing, right? But here you have 8 plus 12. Why the value of k is equal to 16? Here we need pathways from 1 to 15. There are 6 vertices, so 62 is 15. So we need pathways from 1 to 16, 1 to 15. 16 must be equal to 0, 17 must be 1, like that. That is why we have chosen k equal to 16 in this case. Okay. So 8 plus 12 is 20. You take modulo 16, what you get is 4. So 8 plus 12 gives me a path of weight 4. 5 is here, 5 plus 1 is 6, 5 plus 2 is 7, 8 is here, then 9 seems to be missing, right? But we know that 8 plus 12 is already 4, then plus 5 gives 9. You can take 12 plus 8, 20 plus 5, 25 and take modulo 16, what you get is 9. Then plus 1 gives 10 and plus 2 gives 11. 12 is already here. Then 8 plus 5 gives 13. 8 plus 5 plus 1 is 14 and 8 plus 5 plus 2 gives 15. Okay. So here you have all path weights from 1 to 15. Path weights being taken modulo sum as modulo k, where k is equal to 60. So here you have a modular leech tree which is not a leech tree. So definitely there are modular leech trees which are not leech trees, but much is not known. Okay. Again, for modular leech trees, Taylor's condition. That is regarding the order of a modular leech tree. A similar result holds here. Your n will be equal to either k square plus 2 or will be congruent to 0 or 1 mod 4. That it will be either 4n or 4n plus 1 or a perfect square plus 2. Okay. For 8 vertices, it has been proved that there exists only one modular leech tree, and greater than 8, the question is still open. Okay. Again, if T admits a modular leech labeling, then for any edge E in G, there is a modular leech labeling with weight of E equal to 1. Okay. That is, when we consider the case of parts, we restricted ourselves that the weight 1 must be given only to a pendant edge. We cannot give the label 1 to any intermediate edge. Such a restriction was there, right? But such restriction is not there in the case of modular leech trees. If you are sure that there exists a modular leech tree of order n, then you can start by labeling any edge you want with the label 1. It will exist for sure. If at all it exists, it will exist for sure for any labeling with any edge given the value 1. So that is an interesting observation. And now moving on to leaf-leech trees. In leaf-leech trees, the pathways are not taken. We need not give any labeling at all. What we consider is the distance between leaves of a tree. Okay. And this leaves must be at distance exactly 3, 4, etc. NC2 plus 2. So why it is 3, 4, etc.? What happened to 1 and 2? If we insist that the distance between two leaves is equal to 1, then that tree is K2. We can't have anything more. Okay. So that is why 1 is omitted. So what about 2? If distance between two leaves are 2, then that means distance between UW will be equal to distance between V and W. For any vertex W, say distance between two pendant vertices U and V is 2, which means those two vertices are adjacent to a common vertex. From that vertex, there will be a path of say length K to another vertex W. What about the distance between W and U and W and V? Both of them will be always same. So we can't have distinct values. That is why the value 2 is also omitted. Okay. So here we need distances from 3, 4, etc. up to NC2 plus 2, where N is the number of leaves, not the number of vertices, but the number of leaves. If such a labeling exists, we call such trees as leaf-leech trees. So here is an example. Say here 2 examples are there. Distance between U and V is 3. Distance between V and W is 4. And distance between U and W is 5. Okay. And there are 3 vertices. So 3, 4, 5. Those are the only 3 parts, 3 lengths between leaves, and those are all different. Again, this example also, it is easy. You can verify that all weights are at. Is there any relation between leaf-leech trees and trees? Again, properties of leaf-leech trees. Leaf-leech trees also satisfies properties similar to that of leech trees. Since time is running out, I am not going into the details of that. And there is a relation between leaf-leech tree and a leech tree. If you are given a leech tree, I can always obtain a leaf-leech tree from that leech tree by replacing a path, replacing an edge of weight W with W partitions. Okay, so you are giving weight W. Instead of that, I am placing W minus 2 vertices in between, so that the distance between these two vertices becomes equal to W. So, like that, you can always create a leaf-leech tree from a tree. From a leech tree. Okay. Now, the last one, which I would like to mention is almost leech trees. Almost leech trees means one pathway is missing. We need pathways from 1 to NC2, right? So from that one pathway is missing. When one pathway is missing, obviously one pathway will be repeated. That's okay. Only at one place, no. So such trees are called almost leech trees. Here is an example. K14 is an almost leech tree. Here you have 1, 2, 3 is a pathway here as it is an edgeway, and 1 plus 2 also gives me 3. So the label 3 is repeated. Then 3 plus 1 is 4. 3 plus 2 is 5. 6 is missing. Okay, 6 is missing. 7 is there. 7 plus 1 is 8. 7 plus 2 is 9. And 7 plus 3 is 10. Here n is equal to 5. So NC2 is 10. So what we were expecting parts of weight 1, 2, etc. up to 10. Among that, 6 is missing and 3 is repeated. Okay. So this is an example of an almost leech tree. So there are almost leech trees. And almost leech trees also satisfy some relations similar to that of a leech tree. Okay. So to conclude with, these are some open problems which I had already mentioned through throughout the lecture. Just let me summarize. Does there exist any leech tree other than the 5 non-leech trees? 5 leech trees I have already listed. Apart from that, will you be able to find one more leech tree? And let me tell you, there is all possibility that there are no further leech trees. So try to prove that there are no leech trees rather than looking for a leech tree. Okay. Or prove that there exist only finitely many leech trees. We have got 5 leech trees. Maybe there are more. If at all it exists, the number of leech trees is finite. You can prove when you result. How can we do that? Maybe we can prove that if at all a leech tree exists, the order of that tree will be, say, less than 1 lakh. Order is less than 1 lakh means it is finite. Okay. Like that, we can prove that there exists only finitely many leech trees. So, is it possible to prove that? Then determine the value of m of n for n greater than 10, or even a better upper bound for n greater than. The value of a better upper bound for m of n for n greater than 10. Now, identify modular leech trees of order greater than 8. There exists exactly one modular leech tree of order 8. Only up to that. Till date, no one is able to produce a modular leech tree of order greater than 8. But there is all possibility that there exists a modular leech tree. Regarding leech tree, there is no chance that there are more leech trees, but for modular leech trees, there is all possibility that there exists more modular leech trees. Now, does there exist any leaf-leech tree which is not an extension of a leech tree? If you give me a leech tree, as I already mentioned, I can extend it to find a leaf-leech tree. So, using that, we have already obtained 5 leech trees, but not any more. So, does there exist any leaf-leech tree which is not an extension of a leech tree? So, that is also an open question. Okay. So, with that, I conclude. Thank you.
Thank you very much, Dr. Aparna. Yeah. Audience, if you have any question, you can ask now.
Either they understood everything or they didn't get anything.
Let's see.
Hello, ma'am.
Yes, please.
Does this concept exist for directed trees?
You can definitely extend to directed trees. As of now, it is not there in the literature. You can think in that direction.
I was thinking in the direction where if we have opposite edges, we can use -1 so that subtractions are allowed.
That gets cancelled. That is a possibility of extension. In that direction, research is not there yet, but definitely you can think in that direction.
Okay, thank you.
Are there other questions? Okay, I have a question.
Yes.
Can we use some spectral techniques or some algebraic graph theory techniques to show that you don't have leech trees of higher order? Like in strong regular graphs we used to do.
I don't think that spectral techniques will help here
Hmm.
because I'm not sure. How can you relate that? You relate that to labeling. How can you relate a spectral technique to the labeling part?
No, I don't know. Like, is it is it possible to associate a matrix corresponding to the given labeling or given leech tree or any combinatorial object?
Yeah. Yeah, maybe you can think in that direction. Haven't seen any work in that direction. That is taking the say adjacency matrix of tree and trying something there. It is also possible. Maybe in that direction you can settle it.
Okay. Yeah.
As of now, there is no research in that direction.
Okay. Because for construction of strongly regular graph or for non-existence of a strongly regular graph, so I think many of the results are related to that.
Yeah. There is relation, but regarding leech tree, maybe in that direction nobody has yet thought.
Okay.
Maybe that is fine.
Okay. Yes. Are there other questions? Okay, if not, let's thank Dr. Aparna. Yeah, thank you so much, Dr. Aparna. Yeah.
Thank you for the opportunity.